So this video is for those of you who are taking your second semester of physics and you need to study for your final exam. Now, some of the problems in this video might be easy. It might just be a simple review. Some of them will be harder than others. So I'm trying to give you a good overview of what you may need to know on your exam. So let's start with this problem. A dust particle contains 5 times 10 to the 13 protons and 8.5 times 10 to the 13 electrons. What is the net charge of the dust particle in microcoulombs? So feel free to pause the video and try this problem. Now there's a formula that we can use to get the answer. So first, we need to take the difference between the number of protons and electrons. And then we can multiply that difference by the charge of each particle. The charge of a proton is 1.6 times 10 to the negative 19 coulombs. For an electron, is simply negative of that number. So the number of protons is 5 times 10 to the 13. The number of electrons is 8.5 times 10 to the 13. Now, because we have more electrons than protons, we should expect that our answer will be negative. So 5 minus 8.5, that's going to be negative 3.5. So let's take that number and multiply it by the charge of a proton. So the total charge on the dust particle is negative 5.6 times 10 to the negative 6 coulombs. The negative sign simply tells us that there's more electrons than protons in this particle. Now, we need to convert our answer to microcoulombs. 1 microcoulomb is 1 times 10 to the negative 6 coulombs. So this cancels. Thus, our final answer is simply negative 5.6 microcoulombs. So answer choice C is the answer for the first problem. Number 2, a negative 40 microcoulomb point charge lies 8 meters east from a 50 microcoulomb stationary point charge. Calculate the magnitude and direction of the net electric force acting on the negative 40 microcoulomb point charge. So let's begin by drawing a picture. So we have a positive 50 microcoulomb charge, and east of that we have a negative 40 microcoulomb charge. And so that's going to be 8 meters east of the 50 microcoulomb charge. Now, let's talk about the direction of the force acting on the second charge to the right. Let's call this Q1, and the charge on the right, we'll call it Q2. So what is the net force acting on Q2? Now, what do we know about opposite charges? Opposite charges attract. So Q2 will feel an electric force that will accelerate it towards Q1. And that force is directed west. So we could eliminate answer choice A and answer choice D. So we have the direction. Now what we need to do is calculate the magnitude of the electric force. And so we could use this formula to do it. It's K Q1 Q2 over R squared. So K is 9 times 10 to the 9, and the units are newtons, square meters, divided by Coulomb squared. And then we have Q1, which is 50 microcoulombs. So keep in mind, a microcoulomb is 10 to the minus 6 coulombs. And then Q2, don't worry about the negative sign. It's going to be 40 times 10 to the negative 6 coulombs. Since we already figured out the direction, we don't need to worry about the negative sign. Now R is the distance between the two charges. And so that's going to be 8 meters. And don't forget to square it. So the unit coulombs will cancel, and the unit square meters will cancel. So it's going to be 9 times 10 to the 9 times 50 times 10 to the negative 6 times 40 times 10 to the negative 6 divided by 8 squared. And so the force is going to be 0.281 newtons. So the final answer is C. We have a force of 0.281 newtons directed west. Number 3. Calculate the magnitude of the electric field created by a negative 75 microcoulomb point charge at a distance of 50 centimeters east from the point charge. So let's draw a picture. So we have a negative point charge, and let's call it Q1. Now, at a distance of 50 centimeters east, this is going to be the point of interest. So we want to calculate the electric field at that point. Now, let's review a few things. Let's say if we have a positive point charge. The electric field created by this charge emanates away in all directions from the positive point charge. In the case of a negative point charge, the electric field points towards the negative point charge in all directions. So what is the direction of the electric field at point P created by Q1? So the direction is going to be west. It's going to be directed towards Q1. Now, to calculate the magnitude of the electric field, it's going to be KQ over R squared. So K is 9 times 10 to the 9 newtons times square meters divided by Coulomb squared, which I'm going to write as coulombs times coulombs. Q is 75 microcoulombs. Now, because the electric field is a vector and we already know its direction, I'm not going to use negative 75. I'm going to make it positive. R is 50 centimeters. Now, we need to convert centimeters into meters. And you could do this by dividing it by 100. So 50 divided by 100 is 0.5. So R is 0.5 meters. R is the distance between the point charge and the point of interest. So right now we could cancel the unit square meters, and we could cancel one of the Coulomb units. So the electric field is going to be 9 times 10 to the 9 times 75 times 10 to the minus 6 divided by 0.5 squared. So it's about 2.7 million, which we could say is 2.7 times 10 to the 6 newtons per coulomb. So that's the unit for electric field. And this corresponds to answer choice B. Number 4. Calculate the magnitude and direction of the electric force exerted on a negative 80 microcoulomb point charge by an electric field of 4 times 10 to the 5 newtons per coulomb that is directed north. So let's draw a picture first. So let's say we have two charged metal plates. We're going to say the plate at the bottom is positively charged, and the plate above it is negatively charged. The electric field will emanate from the positive plate and travel towards the negative plate. Now let's place a negative charge in the electric field. What is the direction of the electric force that this negative charge will feel? And let's contrast that with a positive charge. A positive charge will feel a force that will accelerate it in the same direction as the electric field. A negative charge will feel an electric force that will accelerate it opposite to the direction of the electric field. So the positive charge will be attracted to the negatively charged plate, and the negative charge will be attracted to the positively charged plate. But make sure you understand that a positive charge accelerates in the direction of the electric field, and a negative charge accelerates in the opposite direction of the electric field vector. So in this case, we know that the negative point charge will feel a force that is directed south and not north. So we could eliminate B and D. Now let's calculate the magnitude of the electric force. The electric force is the product of the electric field times the magnitude of the point charge. The electric field is 4 times 10 to the 5 newtons per coulomb. And the charge is 80 times 10 to the negative 6 coulombs. Once again, we're not going to worry about the negative sign. Notice that the unit coulombs cancel, giving us the unit newtons. So what we have is 4 times 80, which is 320, 10 to the 5 times 10 to the negative 6. You need to add the exponents. 5 plus negative 6 is negative 1. So basically, this is 320 divided by 10, which is 32. So the answer is 32 newtons directed south. So this corresponds to answer choice A. Number 5. Which of the following statements is false? So let's analyze each one. Let's look at A first. Electric field is defined as the force exerted on a tiny positive test charge divided by the magnitude of that charge. Is that true or false? Well, we know that electric field is basically the ratio of force and charge. It has the units newtons per coulomb. So A is a true statement. So we could eliminate answer choice A. Now what about B? Electric potential is defined as the potential energy per unit charge. Is that true? The formula for electric potential is V. And it is the ratio of the potential energy divided by the charge. B is a true statement. Now what about C? 1 volt is equal to a potential energy change of 1 joule per 1 coulomb of charge. That is true. The unit for electric potential is the volt. And 1 volt is equal to 1 joule of potential energy per 1 coulomb of charge. Now what about D? The units of electric field are volts per meter. Now, there are 2 units of electric field. We said that electric field is force per unit charge. So it has the units newton per coulomb. You can also calculate the electric field using this formula, particularly if you have 2 parallel plates, if they're both charged. It's the voltage difference on those plates divided by the separation distance of those plates. So it has the units of volts per meter. So D is a true statement. There's 2 units of electric field you need to be familiar with: newtons per coulomb and volts per meter. So E has to be false. An electron volt is not a unit of voltage. The unit volt is a unit of electric potential, and it's also a unit of voltage. The electron volt is not a unit of voltage, but it's a unit of energy. And that's what you need to watch out for. So here's the conversion. 1 electron volt is 1.602 times 10 to the negative 19 joules. Just as 1 electron has a charge of 1.602 times 10 to the negative 19 coulombs. So we said that 1 volt is basically 1 joule per coulomb. So if you multiply 1 volt by 1 coulomb, you'll get 1 joule. So if we multiply the charge of an electron by 1 volt, we will get the units joules. So 1 electron has a charge of 1.6 times 10 to the negative 19 coulombs. So that's the charge part. If we multiply by 1 volt, we'll get 1.6 times 10 to the negative 19 joules. So this is an electron volt. It's taken 1 electron with a charge of this value, multiplying it by a volt, giving us this energy in joules. Number 6. What is the change in potential energy of an electron that is accelerated from rest through a potential difference of 700 volts? So the fact that the electron is being accelerated tells us that its kinetic energy is increasing. If the kinetic energy of the electron is increasing, that means that it's losing potential energy, which means that the change in the potential energy of the electron has to be negative. So how do we calculate the change in potential energy? Recall that 1 joule is equal to 1 coulomb times 1 volt, or 1 volt is 1 joule per 1 coulomb. So joule is the unit of energy, coulombs is the unit of charge, volts is the unit of electric potential. So it turns out that the change in potential energy is equal to the charge times the change in electric potential, which is also described as the voltage. Q, the charge of an electron, is negative 1.6 times 10 to the negative 19 coulombs. And the voltage is the potential difference of 700 volts. So you can write that as 700 volts, or you can replace the unit volt with joules per coulomb. So the unit coulombs will cancel, giving us the potential energy in joules. So it's going to be negative 1.6 times 10 to the negative 19 times 700. So it's negative 1.12 times 10 to the negative 16 joules. So that's the change in the potential energy of the electron in this problem. Number 7. What is the final speed of an electron that was accelerated from rest through a voltage of 3000 volts? So in the last problem, we said that the kinetic energy of the electron was increasing, and so the potential energy had to be decreasing. When one goes up, the other goes down. So it turns out that the change, or rather the positive change in kinetic energy, is equal to the negative change in potential energy. So let's say if the electron gains 8,000 joules of kinetic energy, it's going to lose 8,000 joules of potential energy. So to make the equation equal to each other on both sides, we need to introduce the negative sign. Now the change in kinetic energy is going to be the final kinetic energy minus the initial kinetic energy. And we know the change in potential energy is basically Q times the voltage, or the change in potential. Now the final kinetic energy is 1/2 mv final squared. The initial kinetic energy is 0 because the electron accelerated from rest. So what we're going to do is multiply both sides by 2 to get rid of the fraction 1/2 on the left side. Next, we're going to divide by m. So we'll have v final squared is equal to negative 2q delta v over m. And then we need to take the square root of both sides. So for this particular problem, the final speed of the electron is going to be the square root of negative 2 times the charge of the electron times the voltage that it accelerates through divided by the mass of the electron. Now let's plug in the data into this formula. So the charge of the electron, we know it's negative 1.6 times 10 to the negative 19 coulombs. The voltage is positive 3,000 volts. The mass of the electron, keep in mind that's still inside the square root. The mass is 9.11 times 10 to the negative 31 kilograms. So go ahead and type it in exactly the way you see it. So you should get 32,462,086, which we can round that and say it's about 3.2 times 10 to the 7 meters per second. So that is the approximate speed of the electron after it accelerates from rest through this potential difference. So D is the correct answer. Number 8. A voltage of 120 volts is applied across two parallel plates separated by a distance of 10 centimeters. What is the magnitude of the electric field that exists between the two plates? So let's draw a picture. This is going to be very similar to the picture that we drew earlier in this video. So here are the two plates, but we're going to put the negative plate at the bottom and the positive plate at the top. And we are going to apply a battery to these two metal plates. So that is the electrical symbol of a battery. The long side is the positive plate, the short side is the negative plate. So let's say we'll call this plate A and plate B. If plate A is at a potential of 0 volts, plate B will be at a potential of 120 volts. The difference has to be 120 because the voltage is 120. So let's say if A was at 50 volts, B would be at 170 volts. B is always 120 volts higher than A. But it's always good to have a reference point. So we're going to say A is 0 and B is 120. Now the distance between these two plates is 10 centimeters. How can we determine the strength of the electric field between the two plates? Keep in mind, the electric field always emanates away from the positive plate and points towards the negative plate. The electric field in this situation is the voltage divided by the separation distance. So it's 120 volts divided by the distance in meters. So we need to convert centimeters to meters. A simple way to do that is to divide it by 100. 10 divided by 100 is 0.1. So the separation distance is 0.1 meters. So 120 divided by 0.1 will give us the answer. So the electric field is 1200 volts per meter. So this tells us that the voltage will increase by 1200 volts every meter. It increases by 120 volts every 0.1 meters. So let's say at 5 centimeters away from plate A, let me draw this better. The voltage will be 60 volts. What do you think the voltage will be 2 centimeters away from plate A? 120 volts divided by 10 centimeters will give us an electric potential, or rather an electric field, of 12 volts per centimeter. So every centimeter, the voltage will increase by 12. So 2 centimeters away, it will be 24 volts. 8 centimeters away from plate A, it's going to be 8 times 12. So it's going to be 96 volts. And so what we have is a potential gradient. As we progressively move from plate A to plate B, the voltage will increase progressively up to 120. So for this problem, E is the right answer. Number 9. What is the electric potential at a point that is 5 meters away from a positive 70 nanocoulomb charge? So let's draw a picture. So here we have the positive charge. We'll call it Q. And at a distance of 5 meters away, at some point P, we want to calculate the electric potential at that point. And it's a formula that we could use. By the way, it's important to understand that the electric potential created by a positive charge will be a positive voltage, or it's going to have a positive value. And the electric potential created by a negative charge will have a negative value. So electric potential is not a vector, it's a scalar quantity. Electric field and electric force are vectors. So when you're adding vectors, that's a whole nother process. But when you're adding scalar quantities, then you could just add them without the use of vectors. The electric potential is kQ over R. Since it's not a vector, we need to incorporate the sign of Q. So for a negative charge, you would plug in a negative Q value. That's giving you a negative potential. K is 9 times 10 to the 9. Q, in this case, is 70 nanocoulombs. Nano is 10 to the minus 9. And R is 5 meters. So 10 to the 9 and 10 to the negative 9 will cancel. 70 divided by 5 is 14. So this becomes 9 times 14. 9 times 14 is 126. So this is the electric potential 5 meters away from the point charge. So A is the right answer. Number 10. What is the electric potential at point P shown in the figure below? And we're told that each point charge has a magnitude of 50 microcoulombs. So how can we answer this free response problem? Well, first, let's call this Q1, Q2, and Q3. So what we need to understand is that every single point charge will create its own electric potential at point P. So the total electric potential at point P is the sum of the individual electric potentials created by each point charge. So V1 is going to be KQ1 over R1, V2 is going to be KQ2 over R2, and V3 is KQ3 over R3. So what we're going to do is factor out a K. Now Q1, it's going to be negative 50 microcoulombs, or negative 50 times 10 to the minus 6. But I'm going to run out of space, so I'm going to see if I can fit it in all here. So we have K, and then Q1, negative 50 times 10 to the minus 6. Now the distance between Q1 and point P is 4 meters. Now Q2, that's a positive charge, so that's going to be positive 50 times 10 to the minus 6. Now what is the distance between point P and Q? So what we have is a right triangle. We have the 3, 4, 5 right triangle. So you could use the Pythagorean theorem to get the hypotenuse. It's a squared plus b squared equals c squared. 3 squared plus 4 squared, that's 9 plus 16, which is 25. The square root of 25 gives us 5. So that's the distance between Q2 and point P. Now Q3, that's going to be negative 50 times 10 to the minus 6. And the distance between Q3 and point P is 3 meters. So go ahead and plug this in. So you should get negative 172,500 volts. So we could see why the potential is negative. It's due to the two negative charges. The two negative charges are a lot closer than the positive charge is to point P. So the fact that we have more negative charges than the positive charge and the fact that those negative charges are closer to point P gave us a negative potential at point P. So make sure you understand that the potential is going to be negative when you're close to a negative charge. It's positive when you're close to a positive charge. Number 11. Calculate the work required to move two 50 Coulomb, or rather 50 microcoulomb point charges separated by a distance of 500 meters to a final distance of 1 meter. So let's begin by drawing a picture. Let's say here's the first point charge, and we're going to say that this charge is stationary. My circles are terrible. And let's say the second point charge is very far away from the first one. So right now the separation distance is 500 meters. We're going to call the stationary charge capital Q, and the point charge that is free to move, let's call it lowercase q. Now I'm going to redraw the stationary charge. Now what we're going to do is we're going to find the work that's required to move the movable charge from a position of point A to a position of point B. So at point B, the new charge Q, or lowercase q, it's going to be a distance 1 meter away from the stationary charge. So how much work is required to move lowercase q from point A to point B? What would you say? Now, by the way, is the work going to be positive or negative? Whenever you move two positive charges closer together, will the potential energy go up or will it go down? As you move it close to each other, you're increasing the potential energy. And as you increase the potential energy, the work being done on a charge is negative. Keep in mind the work energy theorem. Work is equal to the change in kinetic energy. So work is positive when the kinetic energy of a particle or of an object goes up, which means the potential energy is going down. So when the potential energy goes up, the work is negative. So when you're bringing two like charges closer to each other, you're increasing its potential energy. Because once you remove that force, this charge will feel a strong force to accelerate this way. It's kind of analogous to like taking a ball and lifting it up off the ground. As you lift a ball off the ground, it takes a force to go against gravity. So basically, you're increasing the potential energy of the ball. Let me draw a picture. So to lift the ball off the ground, you're increasing the potential energy. It's higher. And once you let it go, gravity is going to bring it back down. That potential energy will now be converted to kinetic. The same is true when you bring this point charge closer to another one. You're increasing the potential energy, and once you let go of that force, it's going to feel a strong electric force that's going to accelerate it to the right. So now, how can we calculate the work required? The work required to move a charge through a potential difference is negative Q delta V. Now keep in mind, this charge will create an electric potential at point A. It will also create a different electric potential at point B. Will the electric potential at A be higher or at B due to this charge? The closer you are to that charge, the electric potential will be higher. So as you move closer to the charge, as the separation distance decreases, the electric potential increases. So delta V is going to be the change in electric potential. It is the electric potential created by charge Q at point B minus the electric potential created by that same charge at point A. Now the electric potential at point B is going to be KQ divided by RB, where RB is 1 meter. That's the distance between position B and charge Q. Now the electric potential at A is going to be KQ over RA. So what we can do now is we can factor out K and Q. So the work required will be negative K times the stationary charge times the movable charge, and then times 1 over RB minus 1 over RA. So now let's plug in the information that we have. So W is going to be negative K, so that's negative 9 times 10 to the 9 newtons per square meter divided by Coulomb squared, or coulombs times coulombs. And then capital Q is going to be 50 microcoulombs, or 50 times 10 to the minus 6. And then the other Q is the same thing, so we can square that number. Now let's put the unit coulombs. And then it's going to be times 1 over RB, which is, RB is 1 meter, and 1 over RA, where RA is 500 meters. So Coulomb squared will cancel, and the unit meters, there's 2 meters here. It's meters times meters, but only one of them will cancel with what we have. So it's going to be negative 9 times 10 to the 9 times 50 times 10 to the minus 6 squared, and then times, in parentheses, 1 minus 1 over 500. So you should get this number, negative 22.455. Now let's talk about the units, because it's always important to understand units. Sometimes you're tested on that information. So right now we have the unit newtons and times 1 of the 2 meters that was here. Notice that it takes 1 meter to cancel both of these because you need to distribute it through the brackets. So right now our answer is negative 22.455 Newton times meters. Now recall that work is equal to force times distance. Force is in newtons, this distance, or displacement rather, that's the more accurate description of this formula, it's displacement. Newtons times meters is equal to the joule. So we could say this is negative 22.455 joules. So make sure you know that 1 Newton meter is equal to 1 joule. Therefore, A is the best answer. Number 12. A 70 microcoulomb charge is placed 4 meters to the right of a negative 120 microcoulomb charge. Calculate the magnitude and direction of the net electric field at a point 9 meters east from the 70 microcoulomb charge. So let's draw a picture. So first we have the negative charge, which we're going to put this on the left. And then to the right of that, there is a positive charge. And the separation distance between them is 4 meters. Now to the right of the positive charge, we have point P. And it's 9 meters to the right of the positive charge. So let's call this Q1 and Q2. So each charge will create its own electric field at point P. Q2 will create an electric field that will be directed away from the positive charge, so it's going to be going towards the right. Q1 will create an electric field that will be pointing towards the negative charge, so it's going to be directed to the left. The net electric field is the sum of these two vectors. Now, because these vectors are going in the x direction, we can add them. E2 is going in a positive x direction, so it's going to have a positive value. E1 is going in the negative x direction, so it's going to have a negative value. E2 is going to be k q2 over r2 squared. Let me write that better. And E1 is going to be k times q1 over r1 squared. So now let's go ahead and calculate the net electric field. So it's going to be 9 times 10 to the 9 times q2, which is positive 70 microcoulombs, or 70 times 10 to the minus 6 coulombs. R2, the distance between q2 and point P, that's going to be 9 meters. Now, K is still the same. Q1 is going to be 120 times 10 to the minus 6. And Q1 is basically a distance of 13 meters away from the point charge. So now let's plug this in. Whoops. 9 times 10 to the 9 times 70 times 10 to the minus 6 divided by 9 squared. So this is going to give us 7,777.7 repeating for this part. And then for the other electric field, 9 times 10 to the 9 times 120 times 10 to the minus 6 divided by 13 squared. That's going to be 6,390.53. So if we subtract those two numbers, you should get 1,387, rounded to the nearest whole number, newtons per coulomb. So this is the magnitude of the electric field. Now notice that this value is positive. This tells us that E2 is greater than E1. So the net electric field will be directed towards the right, in the east direction. Because point P is closer to the positive charge than it is to the negative charge, it's going to field an electric field that will be directed towards the right in the direction of E2. So E2 is going to be greater than E1 because point P is closer to Q2 than it is to Q1. So that's how you can calculate the magnitude of the electric field and determine its direction for a problem like this. Number 13. The 4-point charges shown below are arranged in a square with a side length of 3 meters. Each charge has a magnitude of 200 microcoulombs. Calculate the magnitude and the direction of the net electric force acting on Q4. So first, we need to calculate the force acting on Q4 due to the other 3 point charges. Q1 will cause Q4 to move to the right. So we're going to call that the force exerted on 4 due to charge 1. Q3 is going to pull Q4 towards it. So this is going to be the force on charge 4 due to charge 3. Q2 will also pull the 4th charge towards it. So that's the force on 4 due to charge 2. So we have 3 force vectors that we need to calculate. So let's begin by calculating F for 1. The force between 2 point charges is K times, in this case, Q1 times Q4 divided by R squared. So K is 9 times 10 to the 9. Q1 and Q4, they have the same magnitude, and we don't have to worry about the sign. So we're going to say it's 200 times 10 to the minus 6 coulombs, and we're just going to square it. Now, R, the distance between Q1 and Q4 is 3 meters. So now let's plug this in. So this is going to be 40 newtons. So I'm going to write it above here. F41 has a magnitude of 40 newtons, and the direction, notice that it's east. So let's say east is 0, north is 90, west is 180, south is 270. So it's directed east at an angle of 0. This one is directed south at an angle of 270. And this one is directed southwest at an angle of 225. So for the first vector, we're going to say the angle is at 0 degrees. Now let's move on to the next one, F43. So that's going to be K Q3 times Q4 over R squared. So K is the same. Q3 times Q4, that's not going to change. It's 200 times 10 to the minus 6 squared. Now, we're dealing with a square, so the distance between Q3 and Q4 is still 3 meters. So the math will still be the same. The only difference is the direction. So this force vector has a magnitude of 40 newtons at an angle of 270 degrees. Now let's go ahead and calculate the other force vector. So this is going to be F42. I'm not sure what's happening here. My computer is acting up. This is going to be K Q4 Q2 divided by R squared. So most of this is going to be the same except the distance. The distance between Q4 and Q2 is not 3 meters. What we need to do is draw a right triangle. This is 3, this is 3. What do you think the hypotenuse is? If the legs are the same, the hypotenuse is going to be the length of the leg times the square root of 2. And if you want to confirm that, here's what you can do. Let's call this x. So using the Pythagorean theorem, a squared plus b squared is equal to c squared. So we have 3 squared plus 3 squared is equal to x squared. So that's 9 plus 9, which is x squared. So x squared is 18. And then if we take the square root of both sides, the square root of 18 is basically the square root of 9 times the square root of 2. And the square root of 9 is 3. So you get 3 square root 2. But I'm going to leave x as the square root of 18. So that's going to be r. Now let's replace r with the square root of 18, because once we square it, we're just going to get 18. So it's 9 times 10 to the 9 times 200 times 10 to the minus 6 squared divided by 18. So the magnitude is 20. So F42 is going to be 20 newtons at an angle of 225 degrees. Now our next step is to basically add the components of these 3 vectors. In order to get the resultant vector, or basically the net force acted on Q4, you can call it the sum of the forces, we need to find the sum of the forces in the x direction and the sum of the forces in the y direction. So the net force acted on Q4 is going to be the square root of the sum of the forces in the x direction squared plus the sum of the forces in the y direction squared. So that's how we can calculate the magnitude. For the angle, we're going to use this formula. Arctangent, the y component over the x component. But how do we find the x and y components so that we can take the sum of all of them? Here's what we need to do. So let's draw a picture again. This is F, this is the x component, and this is the y component. the x component is equal to f times the cosine of the angle. And then you could put the unit vector I if you want to. The y component is basically f times sine theta, and it corresponds to, it's usually attached to the unit vector j. So the sum of all the forces in the x direction is going to be basically F 41x plus F 43x plus F 42x. F 41x is going to be 40 cosine 0. F 43x, that's going to be 40 cosine 270. And for the last one, it's going to be 20 cosine 225. So go ahead and type this in. So I got 25.86 newtons. So I'm just going to make a note of that here. And it's positive 25.86 newtons. So let me rewrite that 8 better. Now let's do the same thing for the forces in the y direction. So it's going to be 40 sine 0 degrees plus 40 sine 270 degrees, and then plus 20 sine 225 degrees. So let's go ahead and type this in. So I got negative 54.14 newtons. So at this point, we can get rid of this data here. So this is negative 54.14. So now we can calculate the magnitude of the net force. So it's going to be the square root of the square of the x component plus the square of the y component. And so I got 60 newtons for that. So that's the magnitude of the net force. It's 60 newtons. Now the next thing we need to do is we need to calculate the direction of this force. So let's start with our xy coordinate system. Starting from the origin, the x component is positive. So we're going to travel positive 25.86 units to the right. The y component is negative. So we're going to travel negative 54.14 units down. Now the net force will be in this direction. So it's in quadrant 4. So this is f of x, and that's the sum of f of y. And here is the reference angle. The reference angle is between 0 and 90. So to calculate it, we're going to take arctangent of the y component divided by the x component. Now, even though the y component is negative, we're going to use the positive value so that we get an angle between 0 and 90. So this is going to be 54.14 divided by 25.86. So arctangent 54.14 divided by 25.86 gives us a reference angle of 64.47 degrees. Now, the angle that we're looking for typically is measured from the positive x-axis. So it has to be in quadrant 4, which is between 270 and 0 degrees, 0 is the same as 360. So if a full rotation is 360, we need to go back by 64.47 degrees. So basically, we need to subtract 360 by 64.47 degrees. And so that's going to give us our direction angle. And so that's 295.53 degrees. So now we have our answer. So the magnitude is 60 newtons and the direction is 295.5 degrees measured counterclockwise from the positive x-axis. This is counterclockwise, and this is the direction of a clock, which is clockwise. Number 14. The force between 2 point charges separated by a certain distance is 200 newtons. What will be the new electric force if the magnitude of the first charge triples, the magnitude of the second charge quadruples, and the distance is reduced by half? So we're going to have to use this formula, kq1 q2 over r squared. But for this type of problem, the stuff that doesn't change, we're going to put a 1. So k is a constant, it doesn't change. q1, the first charge triples, so we're going to replace q1 with 3. The second charge quadruples, which means it increases by a factor of 4. And the distance is reduced by a half. 3 times 4 is 12. 1/2 squared is 1/4. To get rid of the fraction, let's multiply the top and the bottom by 4. 1/4 times 4 is 1. And 12 times 4 is 48. So what this tells us is that the force increases by a factor of 48. So the original force was 200 newtons, and the new force is going to be 48 times greater than that. So 200 times 48 gives us the new force of 9,600 newtons. So that's how you can answer questions that basically look like this. So the electric force is proportional to the two charges, and it's inversely related to the square of the distance. Whenever you see an equation like this variable is proportional to everything on top, but it's inversely related to whatever is on the bottom. So as the magnitude of the charges increase, the electric force will increase proportionally. As the distance between the two charges increase, the electric force between them will decrease significantly. So if you double the charges, or rather, if you double one of the charges, the force will double. If you double both charges, 2 times 2 is 4, the force will quadruple. If you double the distance between them, because it's squared, 2 squared is 4, the force will be reduced by a factor of 4. So it's going to be 1/4 of its original value. If you triple the distance, 3 squared is 9, the force will be 9 times less, or it's going to be 1/9 of its original value. So you need to be able to answer questions like that given a formula. Number 15. Which of the following statements is false? So A, the unit of capacitance is the farad. So that is a true statement. That's just something you need to note. B, capacitance is a measure of how much charge a capacitor can store when it's charged by 1 volt. Would you say that's true or false? It sounds true, and it turns out that it is. Q is equal to CV. Q represents the electric charge stored by a capacitor, and Q is measured in the unit coulombs. C represents capacitance, and the unit for that is the farad, and V is the voltage. The unit for that is the volt. So 1 coulomb of charge is equal to 1 farad times 1 volt. Now, if we solve for capacitance, capacitance is basically charge divided by voltage. So a 1 farad capacitor can store 1 coulomb of charge when 1 volt is attached to it. So B is a true statement. A 1 farad capacitor tells us that 1 coulomb of charge can be stored when it's charged by 1 volt. A 1 farad capacitor can also tell us that 8 coulombs of charge can be stored if we attach an 8-volt battery to it. So it tells us how much charge can be stored when a certain voltage is applied to the capacitor. So what about C? A 5 farad capacitor can store 40 coulombs of charge when it's connected to an 8-volt battery. Is that true or false? So using this formula, we have a charge of 40 coulombs when the capacitor is attached to an 8-volt battery. So this gives us a capacitance of 5 because 40 divided by 8 is 5. And so C is a true statement. Let's say if we increase the voltage to 16 volts. That 5 farad capacitor can now hold twice the amount of charge. So for a given capacitor, if we increase the voltage applied to it, we can increase the charge stored on that capacitor. Now let's move on to part D. The capacitance of a parallel plate capacitor is directly proportional to the separation distance. Is that true or false? So for this one, we need a new formula because the one that we have doesn't have the separation distance. So here is a parallel plate capacitor. It's basically two metal plates separated by distance and attached to a battery. A is the area of the capacitor, and D is the separation distance. The capacitance depends on the dielectric material K between the two plates. If it's air, K is 1, and then it's times the permittivity of free space times the area divided by the separation distance. So notice the separation distance is in the bottom of this equation. That means that it's not proportional to the capacitance, but it's inversely related to it. So if we increase the separation distance, the capacitance decreases. So D is a false statement. Capacitance is not directly proportional to the separation distance. It's inversely proportional to it. So D is the answer we're looking for. Now the area of the plates is proportional to it. If we increase the area of the plates of a parallel plate capacitor, wow, my words is just like messed up today. But if we increase the area of those plates, the capacitance will increase proportionally, which means if we double the area, the capacitance will double. If we triple the area, the capacitance will triple because it's a to the first power. Now what about E? Well, E has to be a true statement by default, but let's understand why. So the strength of the electric field created by a point charge is inversely related to the square of the distance. So we have this formula, E is equal to KQ over R squared. Notice that R squared is on the bottom, so it's inversely related. And it's squared, so it's inversely related to the square of the distance. So based on the formula, we can see why that's true. So as you move away from a point charge, as you increase the distance, the electric field will decrease. So if you double the distance, the electric field will be reduced by a factor of 4 because 2 squared is 4. If you triple the distance, it's going to be 1/9 of its original value. It's going to be reduced by a factor of 9. And so that's it for this problem.